Hi guys, welcome to our channel of Honesty Sciences and Mathematics TV channel. In our discussion today, we are going to look at one of the applications for us of Gauss law. And of course, this is a follow-up discussion from the previous number of videos that we've done on Gauss law, its implication on the electric flux, and some of the related topics, of course, that we have discussed on electric field, gravitational field, and of course, we are going to look later at magnetic field, which of course forms a third example of what we had referred to as vector fields. Now, in this case, for a point charge, of course, we're going to consider spherical services of a Gaussian service that we had considered for spherical and cylindrical services in our last discussion. Of course, I'm going to use an illustration in trying to elaborate on this specific concept by trying to depict what basically the concept of a point charge, of course, entail. Now, from the three illustrations that I'm going to give for 1 and 2, of course, they are going to consist of an imaginary surface. And from the second one, this is a three-dimensional illustration. Of course, I hope it's going to be elaborate, that I'm going to use of course, explain the concept of that area that we had given as an area element on the surface of a Gaussian surface, which was basically an area vector. So therefore, for the first case, we're going to consider a spherical surface that is going to contain this radius r from a charge point that I've illustrated as a Q that is centrally located in this specific point. Now, for us to describe the electric field, which are going to be given in this first case, we are going to see that they are going to, of course, be illustrated radially. So in this case, I can just give an example for this. So therefore, the electric field in these specific areas or services are going to be radial in a sense that they are going to emanate from this positive charge going outward. So therefore, in this specific case, then therefore we're going to consider a situation whereby this distance r, which is basically the radius, and this specific point, this radius is going to be the same. The one that I've illustrated, the radius is going to be the same, and therefore we're going to expect the magnitude of the electric fields to be the same. So suppose I give this one to be ij, ej, ei, perhaps an ek. These are not vectors or rather vectors that we normally allocate for ij and k, but just for illustration purposes. And therefore that one means that ei is equivalent to ek. So therefore we are going to see that the magnitude of the electric field across this range of surface, that is distance from the center, are going to be the same. So that one having been said, and therefore we can be able to note that everywhere on this surface, the area vector that we had given as dA, which of course the second part is going to be essential for us. So suppose we have an area vector on this specific surface of a spherical Gaussian surface being illustrated as dA, we're going to see that what we had considered to be the electric field that I've illustrated for E, this specific point is going to be normal to the surface. From our last illustration, I've given that one as N naught. Therefore, E at this specific point is going to be the electric field at these various points on the surface of this sphere is going to be parallel to the area vector, which is given as that. So that we are going to have this one being given as this specific element. We talked about the concept of electric flux will be equivalent to E dA. So doing an integration over this surface, therefore we're going to see that the consequence of this specific assumption, then therefore is going to lead us to a conclusion whereby we're going to see that the magnitude of the electric field at this specific point is going to be constant over the surface, and it's going to be affecting that integral sign, where we're given that the integral of E dA will be equivalent to the integral of E dA. And this basically has an implication of one of the laws of integration that we're going to consider E as a constant, and therefore we're going to take it out of that summation sign. And having talked about this Gaussian surface being an enclosed one, therefore I'm going to use this sign that is encompassing this small circle, this summation sign, showing that this basically is an integration of the surfaces which is enclosed, and therefore I can be able to give this equation in the form of such said E is constant over this radius. Therefore, this is going to be given as the summation over dA. But from a geometrical point of view, this is going to illustrate basically the area of the area of these specific surfaces. And geometrically, we can be able to represent specifically for the sphere, the area of a sphere is going to be given as so the summation of this dA is going to be the area of a sphere, which is given as area is equals 4 pi r squared. Therefore, we can be able to do a substitution for this specific area of a sphere by using this specific formula. So our conclusion is going to be a replacement of this specific aspect, or equating this specific aspect of the formula with area of a sphere. So therefore, we're going to have an integral over that closed surface of E dA, which is going to be equivalent to the total area of a sphere that is going to be given as E 4 pi r squared. So if we try to look at this, then therefore we can have a conclusion whereby the enclosed charge at this specific point is going to be equivalent to the total charge in consideration. So we had given this specific electric flux by looking at the assumption, or rather the description of the Gauss law, whereby we had said that the electric flux can be given as the summation of E dA, which we have given at this specific point, which is basically charge enclosed over the epsilon, as we had of course mentioned in our first discussion on the Gaussian law. Therefore, trying to create the relationship between these three formulae, then therefore we can conclude that basically from Gaussian law, I'm just going to go with this. We can conclude that from Gaussian law, then therefore E 4 pi r squared is equivalent to charge over epsilon naught. We had said that for this particular surfaces, the charge is equivalent to the charge enclosed, which I can just give, of course, such. So therefore, in the equation of this is not going to have an implication on this, since we have equated this specific charge. So therefore, this formula is going to be true, that E 4 pi r squared is equivalent to charge over epsilon, given as such. So if we try to look this as a specific case, then therefore we can have an electric field which is going to be given as rearranging that formula, that is going to give us Q over 4 pi epsilon given as such, and then we're going to have this r squared given as that. So this is going to give a description of an electric field, of course, of a point charge from the relationship between a Gaussian law and the illustration that we have given above. But in one of our videos, we had said that we can be able to include the concept of a constant, which we had given as K. Of course, we had mentioned this in one of our videos, and when especially it pertains to the electric field, it's going to be given as 4 pi epsilon naught, which is going to be giving us a constant. So basically, we can then therefore summarize this specific description for electric field of a point charge Q 4 pi epsilon by taking out this particular section as a reciprocal, which is going to represent, of course, K. Then therefore, this electric field E, this which is a vector field, is going to be described by Ke, which is for the electric field Q over R squared. So this is going to give us a way of describing a point charge of an electric field using the Gaussian law and the related, of course, concepts that we have mentioned. So I hope this is going to form a basis for us in trying to describe other charges. Having said that, basically the relationship between a Gaussian law and a point charge is going to be described using this, especially when it is concerning the concept of its electric field. Now we're going to look at the implication of a Gaussian law and the law of superposition, which is going to consider as an assembly of more than basically two charges and other ways in which we can be able to use the concept of vectors in describing this aspect of charges and various interactions between these different charges and the effect on the electric field. So that is it for now, guys. Check in our description boxes for various videos which are related to this, and of course in assisting us understanding various concepts that we have tackled under the concept of Gaussian law and its related concepts. So that is it for now, guys. Bye, God bless you.